Problem number 1. Dinitrogen pentoxide reacts with water. So, this is a reaction with water because water is the second reactant. And the first reactant is classified as a nonmetal oxide because it's got oxygen and a nonmetal. So when a nonmetal oxide and water react, an acid is produced. So all acids have an H at the beginning. And this acid will be nitrogen based, so there'll be an N in it. It'll be an oxyacid because there'll be an oxygen in it. So you got HNO, but we don't know how many oxygens there'll be. This is going to be a polyatomic ion. And if you look at the polyatomic ion chart, it's either HNO2 or HNO3, nitric acid or nitrous acid. So, to figure out which one it is, we have to check the oxidation state of the nitrogen, which won't change. So, each oxygen here will always have a -2 charge. So the total on this side is -10. To balance the entire thing as an uncharged molecule, the nitrogens must have a charge of +10. So each one will have a charge of +5, except my mouse won't move. Pardon me. +5. So, this nitrogen over here also is +5. And so we have to calculate how much oxygen you need. The hydrogen will always be a +1, and the oxygen is always -2. The total charge over here is +6, and over here, that means this must be -6, so there needs to be 3 oxygens. So the product is nitric acid, HNO3, with hydrogen and nitrate. Now, we're not done yet because it's in water, and nitric acid is a strong acid, so it dissociates. The H goes to H+, and the NO3 goes to NO3-. So, I'll just rewrite the equation, except I can't write, and I'll spare you that, and I'll just separate these two out. H+ and NO3-. We'll delete all this other stuff, and we're done. That's the answer. Problem number 2. Solid potassium carbonate is added to 1.0 molar sulfuric acid. Alright, so K2CO3 plus H2SO4. So, this is an acid-base neutralization. It's in the miscellaneous section because it's one of the obscure ones. What happens here is, since it's a carbonate, it yields carbon dioxide and water because when it mixes with the H2. So you get CO2 plus H2O, and then you get one salt, K2SO4. And those are the 3 products. K2SO4, potassium sulfate. Now we've split it up into ions and removed the less mattering things. So potassium carbonate splits into ions, and so does sulfuric acids, and sulfuric acid is a strong acid. So I'll just split them apart like this. Okay, over here, K2SO4 splits apart, so we'll just split it apart here. Now, the K is the same on both sides, and the SO4 is the same on both sides, so they're spectator ions. We'll just remove them. So what's left is carbonate plus H2 plus hydrogen is carbon dioxide plus water. Now all I have to do is add the charges, remove the unnecessary marks here. Split these apart. So this is CO3 2-, and this is H+, because this is from the acid, and this is left over from potassium carbonate. So there's the reaction, net ionic form. Propanone is burned in air. So a first challenge is to figure out what propanone is. So, propanone is basically an organic material. We have to figure out what it is made of. Now, you see the prefix prop, that means you got 3 carbons. Let's just draw out our propanone here. Here's our 3 carbons. Alright, so this "one" prefix means it's a ketone group. Ketone means there's a double bonded O somewhere in the middle of the carbon chain. Now this carbon chain, there's only 1 carbon in the middle, so you gotta throw your double bonded O right there. And it's easy as that. Just throw on your H's everywhere so all the carbons have their 4 bonds. Yeah, have your H's over here too. And it's easy as that. There's your propanone molecule. We just count up how many carbons there are. 3. How many hydrogens? 6. And how many oxygens? Just 1. So that's fine like that. And we've got our propanone. There it is. Let's get rid of that. Now it's burned in air. Air just means O2, because that's what the burning is. It's burning in oxygen. So, because this is a combustion reaction, burning in air, we know the products are already. We don't even need to think about it. It's just carbon dioxide and water. Just like that. This is how combustion works. The C becomes CO2, the H and the O go to water. And there it is. Students, time for problem 4. Pay attention. Calcium oxide powder is added to distilled water, CaO and H2O. Now, this will result in a base. You know why? Because calcium oxide is a metal oxide. You know that, right? Remember that? Memorize it? You should know this or you will fail the AP exam. Now, we'll write over here, calcium hydroxide, because it is a base. Now remember, does this dissociate? Does it dissociate in water? No, it does not. Remember, never make that mistake. Ever. You must do well on the AP exam to uphold family honor. Amine is shaken with a 0.5 molar sodium iodide solution. Br2 and NaI, the 2 reactants. This is clearly a single replacement because one of them is an element and this one is a compound. Since Br is an anion, then it will go in and take the place of I, which will come out as an element. So yeah, the I2 comes out as an element, and we got the NaBr. Ugh. Yeah, well, now since everything's in a solution, you gotta worry about how everything comes in ionic form. So you have to dissociate everything. This is a ton of useless work. Br2 plus Na plus this is a ton of useless work. I don't know why I have to do it, but you do, whatever. Just gotta separate this two. Alright, you can put that over here and that over here, and we'll make this plus, and this is an I minus. Yay! NaBr. Look, a little piece of the N got eaten by the Br. The Br is a monster. Ah! Ugh. Alright, so you separate them out. You gotta get rid of your spectator ions like Na, because Na is on both sides. It really doesn't do anything. So you got your Br, your I, Br, whatever. Alright. And that's your answer. I better rewrite it so that you buffoons can see it. I hate this class. Oh, terrible. Yep, something like that. Oh man, I've been waiting all day for this descriptive chem moment. Solutions of potassium hydroxide and propanoic acids are mixed. KOH and propanoic acid. Oh, it's time for some organic drawings. See, it's propanoic, so that means it's got 3 carbons, and it's an oic acid, which means it's a carboxylic group, which has an OH and a double bonded O on the end. Oh man, I'm writing so fast because it's amazing. Alright, so you just gotta throw on it's all there. Alright, now count up how many carbons there are. There's 3 carbons. Count up how many hydrogens. 1, 2, 3, 4, 5, 6. 6 hydrogens, and there's 2 oxygens. 2 right here. Now, what type of reaction is this? Well, you've got a base over here and an acid over here, so clearly it's an acid-base neutralization! And every time you get one of those, it's in water. Man, I'm really excited. I wish I could do one of those acid-base neutralizations. Maybe I should mix my car battery with, like, bleach. Man, I'll try this after school. Car battery bleach. I like it. I like it. Alright. So, anyways, well, we gotta put our salt down, which is KC3H5, because one of the hydrogens went into the water, and O2. And there it is. Now, the problem is, we've got to separate everything out into ions. So this is K plus OH minus, and this is K plus C3H5O2 minus. So now we remove our spectator ions. As you can see, K is a spectator ion right here because it hasn't changed on each side. It's K plus on both ends. So all that we have left is this. OH minus plus C3H6O2, and it leads to water, and C3H5O2 minus. Man! Now about that bleach and car batteries. Gotta go run off to do that. I love descriptive chem. So cool. Once upon a midnight dreary, while I powdered weak and weary o'er a many quaint and curious volume of magnesium carbonate. While I nodded nearly eating, strongly there came a heating, as if someone gently decomposing the magnesium carbonate on my chamber door. "'Tis a metal carbonate," I muttered, decomposing on my chamber door, into magnesium oxide and carbon dioxide, and nothing more. Okay, really. So it decomposes into magnesium oxide and carbon dioxide because it's a metal carbonate. And since carbonates, when they decompose, you get carbon dioxide and a metal oxide. And never more. Concentrated ammonia solution is added to copper 2 sulfate solution. NH3 plus CuSO4 yields. This is a complex reaction because the NH3 is because NH3 leads to a complex reaction with copper. Sulfate will be a leftover ion. Now, to find out how many NH3s must attach to the Cu, we look at the charge of Cu, which is 2 plus in this situation, and double it. That means there will be 4 NH3s in the complex. Here I will write it. Now, the complex has a charge. The charge is these 4 NH3s have no charge, and the Cu has a 2 plus, so the whole thing will be 2 plus. And there will be a leftover sulfate ion which has no place anywhere else. It has nowhere to go. Now, because copper sulfate is a solution in solution form, here it will dissociate, which means that this sulfate over here and that over here will both go away. They become spectator ions. So, if you just delete these situations, these are gone, these are gone. This copper is 2 plus, and that is the answer. NH3 plus copper 2 plus yields copper NH3 2 plus for something. I don't know how to read that. It's a complex. Okay, so a hydrochloric acid solution is mixed with a calcium hydroxide solution. Now, this is an acid-base neutralization because hydrochloric acid is an acid and calcium hydroxide is a base. So what this will yield is H2O, water. It'll work just like a double replacement. H2O, water, and calcium chloride. Calcium chloride. So there's your two products. Now you have to split up all the soluble compounds into ions so you can remove the spectator ions. Here, this HCl splits into H plus and Cl minus. We'll just separate them. Calcium hydroxide doesn't split up because hydroxide only splits with barium and strontium, but not with calcium. And calcium chloride will split, so we'll move that over. Now, which ions stay the same on both sides? Chlorine here doesn't move, so I'll just get rid of them. It's gone. And I'll draw the charges on here. Hydrogen plus, Ca2 plus, and that is the reaction. Ta-da! Problem 10, equal volumes of lead 2 nitrate and magnesium iodide are combined. This reaction is double replacement because there are two binary compounds. The result will be magnesium nitrate and lead iodide. Magnesium nitrate. The second result, lead iodide, is a solid. This is the precipitate that makes the reaction possible. Now split the reactants into their ionic forms if they are soluble. Lead nitrate and magnesium iodide both dissolve. The product, magnesium nitrate, also dissolves. Lead iodide stays as a solid. In this situation, the spectator ions are magnesium and nitrate, for these two do not change. Here we will remove them from the equation because they are irrelevant. What is remaining is the actual reaction between lead 2 plus and iodide minus to form lead iodide. Here we are, finally made it to the last problem, problem 11, which is definitely the hardest one. Acidified solutions of potassium permanganate and iron 2 nitrate are mixed together. First, since it's acidified, there's an H+. I'll draw that in. Now, potassium permanganate, which is KMnO4. Okay, and it's mixed with iron 2 nitrate, which is FeNO3 2. Now, what you see here is permanganate, which is a strong oxidizing agent. This means that this falls into the class of reactions known as strong oxidizing reactions. Now these reactions, their final equation will end up with H plus, MnO4 minus, and the third reactant. This K will end up being a spectator ion in the end, so we'll just remove it because we know it to be. So, in these types of reactions, something must be oxidized because permanganate oxidizes. This Mn right now has a charge of +7, but in the end it will end up with a charge of +2. Mn 2 plus. Water is also a product. These are the two products that we know for sure. And there's also an oxidized third reactant. Which one will it be? Well, it could either be nitrogen or iron in this situation. So we have to look at each individual oxidation state. So let's draw out the oxidation states on here. Oxygen is -2. In this one, in nitrate, this entire thing has a -2 charge. Iron here is +2 because it's iron 2 nitrate. So this nitrogen must be +5. So the iron could get oxidized to a +3 state, and iron 3 is also a possible oxidation state. Or the nitrogen could get oxidized, but this isn't a possibility because it's not a metal. So therefore, the iron is the oxidized reactant. The K over here that we had removed could also have been the oxidized reactant, but it can't be because you can't oxidize potassium to a +2 charge or +3. It stays at +1 all the time. So iron is the oxidized reactant. So we'll put it in its oxidized state of iron 3 plus, which means that it has lost an electron. And there it is. There is the reaction. Now we have to remove the spectator ion of nitrate because that never actually changed. So remove that from the picture and get rid of this charge we drew in. So this iron is 2 plus. So this is what happens. There's our reaction. And I'm done with Descriptive Chem project.